Today we're going to talk about internal flow. We, in our convection discussion so far, for the most part, have talked about external flow. So we'll talk about what internal flow is, and then some things we need to change in our modeling approach to deal with internal flow. So if we remember, for external flow, we have, in this example, we have a stationary plate. We have flow that's coming in that's uniform at U infinity. And then as it starts interacting with this plate, you have this boundary layer that grows. So that's fine. You have the boundary layer that's growing, but it would grow indefinitely, right? There's nothing to stop this from growing. It's like, go back to our infinite plane wall or semi-infinite plane wall analogy. In that situation, if you, say, applied a heat flux on the boundary of a semi-infinite plane wall, it would just continue to grow, right? Nothing would stop it. It's the same thing here. You have this like diffusion process that continues to grow. But as we said, eventually it would either become turbulent, or what we're going to talk about today is that boundary layer gets to a point where it starts interacting with other stuff or other boundary layers that are equally growing in. So that's just what internal flow is. Here's, you see the velocity profile. So if we just kind of sketch out, let's say what we're talking about with internal flow, like what defines internal flow. So you have, instead of one boundary layer that's growing like this, you have two boundary layers, like one from the top, one from the bottom, and they both kind of grow in to each other. And eventually they're going to hit a point where they connect or they intersect with each other. And at that point, the boundary layers stop growing, right? They stop changing. And you have this, what's called fully developed flow. So in this region down here, we'll call this hydrodynamically fully developed. Okay, so it's important to think about what that means. So in this region here, the boundary layer is growing. So I guess a delta M. So this is a momentum boundary layer, delta M up here. So you have this momentum boundary layer that's growing. At this point, once you're fully developed, stuff will stop changing, right? There's no longer anything that's, say, causing shear stress to be a function of position. Shear stress is going to be based on the same delta M, so that stops changing. It's fully developed in that if I pick any point beyond this cutoff and look at the shear stress, it's going to be the same value. That's really the definition of internal flow. At some point, you're fully developed. So let's, I guess, talk a little bit further about that shear stress. So if we plot it out, let's see, draw a plot here. So if I plot it out as a function of position x, the shear stress, the local shear stress, so tau x, if I did that for, let's say, external flow, let's start here. So external flow at the leading edge of this plate or whatever, you're going to have this infinitely thin delta M, and so your shear stress is effectively infinite. So you have shear stress that is infinite, but it quickly drops down and kind of tapers off. Okay, something like this. It's going to keep tapering off. For internal flow, let's say there's some position here which we call, let's call this position down here x, fd, h. So that's the fully developed position hydrodynamically. So if we looked over here and picked some position x, fd, h, and then now plotted the shear stress for internal flow, what would that look like? Well, you'd have the same kind of thing where you, let's see, pick a different color here. So you have the same kind of thing where you come down and it sort of follows along. But then as it approaches this point, it starts to separate. And at that point exactly, it will become perfectly flat. Right. Now the shear stress will stop changing. So this is external, or sorry, internal, and this was external. Okay, So that's, I guess, the core concept of internal flow. Let's look at the velocity profiles that go along with this and just kind of see, here's our velocity profiles for external flow. Let's look at how the velocity profiles change at these different positions. One thing I want to just mention before we move on, this is called the fully developed region. This is maybe obviously called the developing region, right? So if you're creating a model of, say, pressure drop or heat transfer coefficient or whatever, the big question is usually, is this developing region, is that an important part of my overall length? Like, is the pipe 100 meters long and this happens in the first centimeter? If so, usually you can neglect that, right? It's not important. If it's, this is a third of the length, then it's important because you have this really big entrance effect that doesn't get washed away at all. So let me just write, this is the developing region. Let's see, this is the developing region over here. Okay, so the velocity profiles, go to the next slide here. So let's maybe re-sketch this, get something here. So we have our top wall, we have our bottom wall, and let's draw some boundary layers that are growing here. Maybe this would look like this, and this. Okay, so if I picked a position, let's say here, you can see that a little bit. So I'm going to pick a position here. I want to draw what the velocity profile looks like. We have coming in, I guess maybe to start, let's say coming in on this edge, with the leading edge, you have U infinity. So I'm going to draw, oops, I don't want to do that. So I'm going to draw this here. So I guess it would look something like this. You're going to have a velocity profile at the wall that has the no slip condition, so the velocity is 0 there. And then as you go up, it starts to kind of taper off like this, right? So aligned with this point here would be a position where the velocity would be constant in that kind of center core. So then it's constant across here. And then it's going to do the same thing on this edge, right, where you have this kind of thing. So this would be our velocity profile at this position. Stuff to maybe point out. So obviously you have what's sort of looks like your normal velocity profile for our external flow. One question, I guess, is we have a slower velocity here because of the no slip condition, right? The velocity near the plate has slowed down. So the velocity in the middle, is that U infinity or something else? It's going to be faster. It has to be faster, right? Because you've forced stuff near the edge to go slower. You have a constricted volume. Therefore, the stuff in the middle has to go faster to compensate for that. Right? So as you go along, the core kind of accelerates a little bit. And that becomes important when we're talking about conservation of momentum. So okay, that's that position. I guess let's pick, let's look right at the position here where the boundary layers merge. So what does the velocity profile look like there? Well, I guess it would look like kind of like this. And then the same thing on the other end. So again, you have the no slip condition. But right at the middle where they meet, I guess you have the same velocity slope. So right at that position. So it's this kind of parabolic shape that's perfectly symmetric. That's maybe fairly obvious. So then let's maybe pick a position you're further down along in this direction. What is the velocity profile going to look like there? Yes, exactly. Once you get to this point, it stops changing. So it's exactly the same. So it would be, again, like this. Same thing as the other one. Let's see. So let's give some labels here. So this is our momentum boundary layer, delta M. This is our boundary layer thickness, right, delta M. For x is less than x fd comma h. Sorry, that's bad. Try that again. Be a better judge of the space I have available. Okay, so this is delta M for x is less than x fd comma h. Here at this position, I guess we have delta M at x fd h. Right, and that's the same in all subsequent positions. This velocity, let's see, this velocity right here is higher than this velocity, or is higher than this velocity, I mean to say. So the core continues to accelerate. That's the highest velocity. That's kind of your maximum velocity in the flow. What else? So we can say in terms of x position, let's maybe label some x positions here. So this x position here is called x fd h, which we already noted. And then if you want to be able to compute the bulk mean velocity, which is important, so bulk mean velocity, the bulk mean velocity is going to be given to you or computed as u sub m equals the mass flow m dot divided by rho times AC, or alternatively, the volumetric flow rate v dot over AC. So that's just a way of saying what's my average velocity in this profile. And that doesn't change, right? That average velocity is not going to change as a function of position, but you do get a redistribution as you move forward.